Okay, in this video, I would like to introduce another type of aggregation and segregation producing um, models. Also, you can consider uh, this type of model as another variation of IPS. It's called voter model or voter models. So it it knows the basic framework of IPS, localized birth and death processes, right? And in other IPS models I introduced, we use delta and beta to decide birth and death, right? And also you can consider this type of model, voter models, as another variation of ISP because the state of each cell depends on the majority of states in neighborhood. That is actually a property from IPS, right? Because beta is decided by the fraction or the proportion of living neighborhood living neighbors, right? And also we have seen another type of voter mode. It's called deterministic voter mode. It's actually majority say A, right? Each cell will switch to neighborhood mode, okay? Which means that for each cell, we just need to know which state is the majority within the neighborhood. Then we will simply switch the state of the central cell to that state, right? So it's deterministic. There is no probability in this switching process. But IPS is a stochastic model. And the state of the central cell is based on fractions of neighborhood states, right? Of course, that's beta, right? And also, we can simply give us a set probability or set or a fixed rates, right? Instead of using the proportion of the neighborhood of living neighbors to decide a beta value, we can simply say, okay, 50%. With a probability of 50%, a dead cell is going to be alive after next tick. And this 50% has nothing to do with the neighborhood, right? That's fixed rate, okay? And 3.8 in the model library is the voter model. It's a demonstration of voter model in NetLogo, and it is a model with probabilistic transformations based on fractions of neighborhood states, which means here we still have beta instead of a fixed rate to decide if a cell is going to be alive after next tick. And there is a switch in this model when you play with it. It's called sequential updating. If you turn it on, although I mean this model will still, no matter you switch it off or on, the model will follow the asynchronous updating method. But if you turn it on, this model will update cells one at a time. That's asynchronous. But from left to right, from top to bottom on the lattice, instead of randomly choosing one to update, right? By default, if you are using asynchronous updating, you just simply randomly choose a cell and update and repeat this process until the number of this process is equal to the number of cells on the board. That's called one generation, right? But you can still use something called sequential updating to give a specific sequence for updating cells. Okay, here is the code. Here is the code patch for implementing this sequential updating. Okay, it's a little bit special, so I paste it here. Okay, and another type of voter model is called random walks. Okay, and random walk is the main character of next what of next chapter. Okay, random walk, and state transitions can be viewed as states moving from one cell to another cell, which means you can consider a specific cell as a what, as a walker, right? It is going to walk through the space from a starting point, of course, and following specific rules. It is going to walk within the space. We call it random walk because there is randomness in this process, but it's not purely random because after all, we're going to set some rules to guide this specific individual to walk. Okay, random walks have known mathematical properties, and these properties can tell us about long-term behavior of voter model. Okay, a lot of phenomena can be addressed by random walks model. For example, the foraging behavior of animals. Okay, here I'll just give you the concept here and addressing the relationship between voter models and random walks. You should know that random walks models, they are a part of voter models. Okay, and random walk models, they have other properties. For example, consensus state. In one or two dimensions, okay, the system will reach a consensus in which all sites are in the same state, which means that, okay, for example here, initially there were 8 states, and after maybe a very long time, there will be only one state. Because due to the property of voter model, which means that there is always vote, and usually majority. I mean, not usually. It's majority winning. Okay, eventually there will be a winner. There will be a consensus state. Okay, and this state is absorbing, which means that once entered cannot be exited. This is a stable condition or a stable state of the system. Okay, and also cluster size growth. Before the consensus state, there was say there are different clusters. Some of them they are larger, some of them they are smaller, and cluster sizes grow with the square foot of elapsed time. There is this mathematical relationship between the size of clusters and time. Okay, and also we can add even more randomness into voter models. For example, random switching of states with non-adjacent sites. Okay, at a specific time, you choose a cell randomly and choose another cell randomly away from the first cell you just chose with a random direction, with a random distance, and you simply switch the states of them. Of course, if they are in the same state, switching is meaningless, but whatever, you can do this, right? To add some more randomness into your simulation, okay? Simulates nested spatial interaction and disrupts formation of large clusters even at low probabilities. Okay, because the cell you chose as the first one could be in the center of a cluster, and another one could be very far away from the cluster with a different state. When you switch the states of them, there is disruption in the center of this cluster, and that disruption could spread out. Okay, and but eventually system will still reach a consensus. One state will win. Okay, and another method to add noise mutation is called random mutations of states. Simulates random error. Okay, it means that you don't do switching. You don't do switching. You simply randomly randomly choose a specific cell and give it another random state. Could be the state it is in right now. Could be another state. This is dependent on your specific application. You can decide, but this is actually adding purely random noise into your simulation. You will say, why would I need noise in my simulation? I mean, that's because in real world, when the real processes they are happening, there could be random noise, and you cannot avoid that. So actually adding random noise into your simulation is making your simulation more real. Okay, and here 3.9, that's another NetLogo model you can find from Carmen, in the Carmen. For voter model with mutation or with noise. Okay, so here here is the end of 3.4 IPS systems. And from next video, I'm going to start introducing scaling models. Okay, it's another important type of models producing aggregation and segregation. Thank you.